Don't answer! Don't answer! Don't answer! Netflix's The Three-Body Problem is finally out. Is contacting aliens safe or risky? In fact, humans have often tried to contact alien civilizations. Even that technology in three-body has been proven. Who will contact aliens first, China or the US? Next, we might spoil the original novel's setting, but shouldn't spoil the Netflix show. If you're also curious about contacting aliens, let's see how far humans have flirted with them. Have we contacted alien civilizations? On contacting alien civilizations, opinions vary. Three-body author Liu Cixin suggests humanity is too weak, better avoid contacting aliens to dodge unnecessary risks. But back to reality, if we were in the three-body world, humanity truly tempts fate. In 1974, scientists used the Arecibo Observatory to send the famous Arecibo message to the M13 star cluster. The target, not far with many stars, is considered a potential alien civilization's hub. The message included human DNA, the solar system, human figures, feels like a chicken shop's flyer campaign. Beyond intangible radio messages, humans sent a tangible letter to space. In 1977, Voyager carried the golden record into space. The record has greetings in 55 languages, sounds of nature, 115 images, and the solar system's location via 14 pulsar. A letter of human civility and friendship to the universe. Well, if the receiver isn't friendly, then even cautioning against contacting aliens might be too late. Whether they're good or evil, whether they might attack, we can only leave it to fate. But after so long, have we heard from aliens? To confirm alien life, receiving signals is as crucial as sending, even more so. In 1960, astronomer Frank Drake used Project Ozma with a 26 meters radio telescope to observe stars Epsilon Eridani and Tau Ceti, marking SETI's inception. Sadly, despite over 150 hours of messages, no discernible signals were found. The more recent Project Phoenix in 1995 aimed to study radio waves between 1,200 and 3,000 megahertz from 1,000 stars near the Sun. With funding, SETI spends $5 million annually to scan over 1,000 stars, yet has found nothing so far. In a twist, in October 1967, Cambridge's Jocelyn Bell detected regular pulses via a radio telescope, 1.34 seconds intervals lasting 0.04 seconds each. Due to its potential extraterrestrial origin, the signal was jokingly named Little Green Man 1, LGM1. However, similar pulses were later found, confirming they came from rapidly spinning neutron stars, not a civilization sending messages. China also seeks extraterrestrial life. The Guizhou Fast Telescope is highly watched. Its diameter reaches 500 meters. It's Earth's largest single-dish radio telescope. FAST isn't just rumored in alien search. After launching in September 2016, FAST joined SETI. Interstellar communication is a key task, aiming to catch signals from alien civilizations. With the title of Earth's largest telescope, it draws much attention. Since 2016, it's spotted many suspicious signals. However, these signals must be verified, ensuring they're not from terrestrial sources or previously undetected radiations. Officially, no alien signal has been confirmed. But did we choose the wrong communication method? Even if electromagnetic waves carry messages at light speed, the solar system spans 2 light years, the Milky Way 100,000 light years. Our messages might take ages to return, not to mention physical letters cast into space. Voyager 1 was once the fastest man-made object, still moving away at 60,000 kilometers per h, just 1/18,000th of light speed. Even heading to the nearest star, Proxima Centauri, it would take about 76,000 years to arrive. Messages via electromagnetic waves could be blocked or absorbed by dust, planets, stars. Whether human or alien, we need a fast, enduring signal, ideally traversing obstacles at light speed. The three-body problem suggests a key: neutrino communication. What is neutrino communication? Neutrinos, often called in China, are fundamental particles, the basic units of matter, indivisible. They've garnered wide interest due to their weak interaction and high speed. Neutrinos easily pass through most materials almost unimpeded, making them hard to detect. In the universe, neutrinos are second only to photons, making them the second most abundant particles. How many? Per square centimeters facing the sun on Earth, about the size of your fingertip, is pierced by 65 billion solar neutrinos each second. That's how many. But their reaction with matter is very weak. For example, in pure water, they'd travel 250 light-years on average for a single interaction with water, making their presence almost undetectable. Physicists find neutrinos' three flavors special, namely electron, muon, and tau neutrinos, each with unique physical properties. The standard model in particle physics describes three fundamental forces and all basic particles. Here, neutrinos are considered massless. However, discovering neutrinos have three flavors and oscillate among them proves they have mass, overturning their supposed masslessness in the standard model, showing it's incomplete. Neutrinos are of great research value in physics, worth a full episode's exploration. This is just a brief intro. If you're interested in neutrinos or other particles, feel free to urge us in the comments. Just know, neutrinos not only overturn the standard model, but their mass as the universe's second most abundant particles could reshape our cosmic understanding and enhance dark matter insights. But back to our question, if neutrinos barely interact with particles, how do we receive neutrino communications from aliens? In the Netflix 3-body trailer, the fleeting scene with golden spheres in a large tank with a sci-fi and slightly religious vibe is key. Not explicitly mentioned in the novel, but some viewers might have noticed. Located in Hida, Gifu Prefecture, Japan, 1,000 meters underground, is the repurposed abandoned mine, now the large neutrino detector Super Kamiokande. The detector's main structure is a 41.4 meters high, 39.3 meters diameter giant cylindrical tank. Its inner walls are fitted with 11,200 photomultiplier tubes to capture faint signals. The tank is filled with 50,000 tons of ultra-pure water. Neutrinos are detected by waiting for them to pass through the detector, interacting with hydrogen and oxygen atoms in the water, producing a faint blue glow. This is similar to the blue glow in nuclear fuel pools mentioned in our nuclear series, occurring when particles exceed the speed of light in water, creating a sonic boom-like Cherenkov radiation. In short, scientists use a massive water tank to interact with neutrinos and employ over 10,000 photomultipliers to capture faint Cherenkov radiation signals. But this design is truly valuable, as the mentioned neutrinos can convert among three flavors proven in this tank. Post-construction, the Super Kamiokande nurtured 5 Nobel laureates in physics for Japan over 40 years. The 3-body series filming here was indeed a stellar choice. That said, with neutrino detection methods established, real-world research on neutrino communication began. How is neutrino communication achieved? Teams from the University of Rochester and North Carolina State University published a paper in 2012 explaining they successfully used neutrinos to transmit a message over 1 kilometer, 240 meters of which was through solid rock. The message was neutrino. Setting up the equipment was no small feat, involving the powerful particle accelerator NUMI. Protons were accelerated around a 3.3 kilometers track, colliding with a carbon target to emit a high-intensity neutrino beam. The neutrinos were received by the hexagonal detector Minerva, 1.7 meters by 5 meters, located in a cave 100 meters underground. Naturally, both setups were primarily for neutrino research, not specifically designed for communication. The team utilized a gap between main tasks, spending 2 hours to verify communication feasibility. But with neutrinos being hard to detect, how can they be used for communication? The team shifted their approach to transmit just 0 and 1, where 0 means no neutrino emission and 1 indicates the emission of many neutrinos. So many that even if only 1 in 10 billion is detected by Minerva, the sheer number ensures detection. The final result was an average transmission of 0.1 bits per second, with a 1% error rate. Though not practical yet, it's a good start. Neutrinos can penetrate almost anything, making them useful beyond contacting extraterrestrials. They have other potential uses, like communication for submarines or with deep underground mines. Moreover, they could enable point-to-point straight-line communication without worrying about obstructions. Regarding the space race, they could solve communication issues on the far side of the moon perfectly. So, how is the progress in neutrino research globally? Beyond the previously mentioned Super Kamiokande, there are several intriguing neutrino detectors worldwide, like the Sudbury Neutrino Observatory, SNO, in Canada, featuring a unique spherical design filled with heavy water specifically to observe solar neutrinos. The IceCube Neutrino Observatory in Antarctica buries its detectors in the Antarctic ice between 1,450 to 2,450 meters deep, using the overlaying ice as a neutrino capture medium. A clever design making IceCube the largest neutrino detector on Earth. In addition to these operational detectors, the US, China, and Japan are all developing more advanced and powerful detectors. The Deep Underground Neutrino Experiment, DUNE in the US, is expected to become the world's largest cryogenic particle detector. The receiver is located a kilometer underground in South Dakota, with the neutrino signal for research coming from Fermilab, 1,300 kilometers away, where a megawatt-class proton accelerator will generate the strongest neutrino beam ever. The acronym for this Deep Underground Neutrino Experiment is quite interesting. It's DUNE like the dunes. In China, the Jiangmen Neutrino Observatory is planned for Jiangmen, Guangdong, using 20,000 20-inch photomultiplier tubes and 25,000 3-inch ones to build a massive spherical neutrino detector 700 meters underground. It can be filled with 20,000 tons of pure water. The latest news anticipates it will be operational by 2024. Lastly, the iconic Super Kamiokande is not standing still, with Japan planning an even larger Hyper Kamiokande detector. The volume will increase by 5.2 times. Photomultiplier tubes will increase from 11,200 to 40,000 to further study neutrino and anti-neutrino oscillations. The goal of these neutrino detectors is to study neutrinos' properties. But since neutrino communication is possible, researching this possibility outside of missions is not out of the question. Although we haven't contacted our neighbors yet, I sincerely hope they're friendly. But it's hard to say when an alien civilization might finally receive our messages, greet us with neutrino communication, or even come to Earth following our signals. What should we do then? Our website features several articles, including an introduction to the dark forest theory and how to communicate with aliens with whom we share no common language as seen in Arrival. Interested friends can click the link in the information bar to view. Finally, do you think we should actively contact alien civilizations? A. Absolutely, I believe exploration is always positive, and I think gravitational wave communication is more promising. B. Not yet. I can already imagine being enslaved by alien civilizations. C. To maintain the balance between the US and China, Taiwan should take the lead in contacting aliens, no doubt. Alright, that concludes this episode. Remember to subscribe to the PanSci channel, turn on notifications, join our channel membership, and stay tuned for more exciting science news and topics. See you next time.